Welcome back, guys. I'm Professor M.S. Patil, and in this video lecture, we are going to talk about the design of shaft. In the previous video lecture, we have discussed about what are shafts, what are the different types of shafts, and what are the different materials that can be used for manufacturing the shaft. Now, in this video presentation, I'm to talk about the design of shaft subjected to different kinds of load. What are the learning objectives of this session? In this session, we are going to talk about the design of shaft, and then we will design the shaft on the basis of ASME codes also. Now, talking about the design of shaft can be designed on different bases. First basis is strength basis, where we are talking about the safety of the shaft on the basis of comparison between the induced stresses and permissible stresses. Then we are going to talk about the design of shaft based on torsional rigidity, that is the angle of twist. It should not exceed the permissible limit. And then we are going to talk about the design of shaft on the basis of lateral rigidity also. That means the deflection of the shaft due to the lateral loads. On the basis of strength, shaft can be designed which are subjected to axial loads. That means the load is acting on the axis of the shaft. When lateral loads are acting on the shaft, then the shaft is supposed to bend, and due to the action of the bending moments, bending stresses are getting induced. We can design the shaft on the basis of twisting moment while transmitting the torque. The shaft twist and shear stresses are getting induced in the shaft. We can design the shaft on combined bending and twisting moments also, where we are going to use two theories. One is principal stress theory and one is maximum shear stress theory. Now, talking in details about all the bases, that is strength basis on axial loads, bending moments, twisting moment, and combined bending and twisting moment. So, starting with the design of shaft on the basis of strength subjected to axial tensile force. So, when the shaft is subjected to axial tensile force, then the tensile stress is given as force upon cross-sectional area. If we call the diameter of the shaft as small d, then the cross-sectional area of the shaft will be pi by 4 d square. And therefore, sigma t will be equal to p divided by pi by 4 d square. And we can simplify the equation as 4p upon pi d square, where p is the axial tensile force, d is the diameter of the shaft, and sigma t is the tensile stress. This sigma t can be obtained using the principal stress theory, that is SYT divided by factor of safety. One thing should be noted, we will not use ultimate tensile stress in this case because shaft is made up of ductile material and therefore yield stress is going to govern the things, and therefore sigma t will be calculated as SYT divided by factor of safety. Again, on the basis of strength, when the shaft is subjected to pure bending moments. From where these bending moments will come on the shaft is necessarily transmitting power, and for power transmission, gears and pulleys are mounted on the shaft. And therefore, the weight and the resultant forces of the gears and pulleys, belt tensions, they will be inducing the bending moment in the shaft material, and therefore we have to design the shaft on the strength basis subjected to pure bending moment. Here we are going to use the flexural formula, that is m upon I is equal to sigma b upon y, and simplifying the things we will get sigma b is equal to mb into y upon I, where mb is the maximum bending moment, y is the distance of extreme fiber from neutral axis, that will be d by 2, and I is the moment of inertia, that will be calculated as pi by 64 d raised to 4, because the cross section of the shaft is circular. Therefore, the moment of inertia about the neutral axis Ixx or Iyy is the same, and that is pi by 64 d raised to 4. Simplifying the things, we can get this equation sigma b is equal to 32 mb upon pi d cube, where mb is the maximum bending moment, d is the diameter of the shaft, y is the distance of extreme fiber from neutral axis, and I is the moment of inertia. Again here, the permissible bending stress sigma b is calculated as SYT divided by factor of safety. Talking about the design of shaft on the basis of strength subjected to pure twisting moment, torsional moments or torque. Here we are going to use the torsion equation. Mt by J is equal to tau upon R, and therefore tau is equal to Mt into R upon J, where Mt, many a times Mt is also called as capital T torque, but here I'm going to use the notation Mt as torque or twisting moment or torsional moment. Okay, then R is d by 2 and J is the polar moment of inertia, pi by 32 d raised to 4. Simplifying the things, we will get 16 mt upon pi d cube as the equation for the permissible shear stress. We can be calculated from maximum shear stress theory. Tau is equal to 0.5 SYT divided by factor of safety. Here, the notation mt is maximum twisting moment or torque, d is the diameter, r is the radius, j is polar moment of inertia. Tau is the permissible shear stress, which is 0.5 SYT divided by factor of safety, where SYT is the yield strength of the material. Now, when the shaft is subjected to combined bending and twisting, that means second criteria and third criteria, if we combine them, right, then the loads are acting in different directions, and therefore we have to take help of the theories of elastic failures. Okay, so here sigma x is equal to sigma b is equal to 32 mb upon pi d cube, as we have seen earlier, and tau is equal to 16 mt upon pi d cube. So first theory here we are going to use is maximum principal stress theory, where the principal stress sigma 1 is given as sigma x by 2 plus under root of sigma x by 2 whole square plus tau square. This equation we can we have already learned it in strength of materials. We can refer any book of strength of material for this equation. So putting all the values in this equation, we'll get the simplified equation as sigma is equal to 16 upon pi d cube mb plus under root of mb square plus mt square. This term in the bracket is called as equivalent bending moment. We can have this equation, the expression mb plus under root of mb square plus mt square, which is called as equivalent bending moment. So it will be 16 times equivalent bending moment divided by pi d cube, where this sigma 1 according to principal stress theory is SYT divided by factor of 70. So comparing this equation and this equation, we can obtain the diameter of the shaft based on maximum principal stress theory. Similarly, second theory is maximum shear stress theory, where we can have the equation of maximum shear stress as under root of sigma x by 2 whole square plus tau square. Again, this equation can be referred to any book of strength of material. We have already studied it in strength of material. We can obtain it from any book of strength of material. So putting all the values again for sigma x and tau, we can have the simplified equation as 16 upon pi d cube under root of mb square plus mt square, where this term in the root under root of mb square plus mt square is referred as equivalent twisting moment. So tau max is equal to 16 times equivalent twisting moment divided by pi t cube. And according to maximum shear stress theory, tau max is calculated as SSY upon factor of safety, where SSY is the yield stress and shear, which can be calculated as 0.5 SYT upon factor of safety. Here onwards, we will be calculating tau max as directly 0.5 SYT divided by factor of safety. So comparing equation 1 and equation 2, we can obtain the diameter of the shaft. As already told, the term under root of mb square plus mt square is called as equivalent twisting moment. So these are the two theories of elastic failures which are used to calculate the diameter of the shaft when it is subjected to combined bending and twisting. Now the next criteria for the design of the shaft is on the basis of torsional rigidity. Again, we will be referring the torsion equation, and the first and third term mt by g is equal to g theta upon l. Rewriting the equation, we will get theta is equal to mt into l upon g into j, where theta is the angle of twist in radians. So when we are converting radian into degree, we have to multiply it by 180 by pi. So now theta is in degrees. If we have a solid circular shaft, then J is pi by 32 d raised to 4. Combining these two equations, we can get theta is equal to 584 mt into L divided by g d raised to 4. So these are the standard notations which are used in this equation. Theta is the angle of twisting degree. L is the length of shaft subjected to twisting moment, not the entire length of the shaft, only the length of the shaft which is subjected to twisting moment. Mt is a torsional moment or torque as it is popularly known. G is the modulus of rigidity or shear modulus, and D is the shaft diameter. Other than this, we can also calculate the diameter on the basis of ASME codes. On the basis of ASME, right? ASME codes, what these codes say, that the permissible shear stress is equal to 0.3 times SYT or 0.18 times SUT, whichever is minimum. And if a keyway is present on the surface of the shaft, the strength of the shaft can be reduced by 25%. So again, multiplying it by 0.75 and taking the minimum value will give us the permissible shear stress. Remember, 0.3 times SYT or 0.18 times SUT, whichever is minimum. Again, if keyway effect has to be considered, then reducing these values by 25%. Therefore, remaining strength will be only 75%. So here onwards, we will be multiplying these equations by 0.75. Again, according to ASME codes, shafts are always designed on the basis of fluctuating loads. Mind, there is difference between the static load and the fluctuating load. In the static loading condition, the magnitude and direction and the point of application of the load remains constant. But in case of fluctuating loads, either the magnitude or the direction may change. Therefore, according to the American Society for Mechanical Engineers and their codes, we have to always design the shaft on the basis of fluctuating loads. So in order to account this varying nature of load, we have to consider two factors, KB and KT. KB is the combined shock and fatigue factor in bending, and KT is the combined shock and fatigue factor in twisting, respectively. So KB should be multiplied by MB and KT should be multiplied by MT, that is torque. And therefore, when we see here, again, the most important thing, as I already told, that the ASME codes always say that the shaft should be designed on the basis of maximum shear stress theory of failure. So this equation already we have seen in the previous slide, tau max, according to maximum shear stress theory only. So we are not going to talk about sigma, we are going to talk about tau max. So the previous equation was tau max is equal to 16 upon pi d cube under root of mb square plus mt square. But in order to account for the fluctuating loads, mb should be multiplied by kb and mt should be multiplied by kt. Therefore, the equivalent twisting moment, this term under root of kb into mb whole square plus kt into mt whole square, here it will be a new equation for the equivalent twisting moment, right? And therefore, here the meaning of kb and kt is given, combined shock and fatigue factor to bending for bending and twisting respectively. And the values of kb and kt, they can be obtained from this table, which are based on the type of load applied. If the load is gradually applied, then these values will be taken. If the loads are suddenly applied with minor and heavy shocks, then the values can be taken in this range. So this was related to the design of shaft based on different criterias. Now in the next lecture we will talk about the design of hollow shaft, because in this video presentation we have seen the design of solid shafts only. Now in the next presentation, in the next video session, we will talk about the design of hollow shaft, and then we will solve the practical based numericals. Thank you for listening the video very patiently. Good day to all of you. Thank you.